Good afternoon and welcome to today's webinar, eMobility Tech Outlook 2026, the technologies powering the next generation. My name is 𝗍𝗲𝗲𝗰𝘁𝗶𝗰 and I'm the Senior Content Manager for CWIEME Berlin. We are delighted to have you joining us today and hope you enjoyed the presentations and the opportunity to connect virtually with your peers across the industry. Before we begin, I would like to briefly cover a few housekeeping points. If you have any questions during the session, please submit them in the comment section. This webinar will be available on demand after the session, and the presentation slides will be available for download on our website. Now it's my pleasure to introduce today's speaker. We have an exceptional lineup of experts from S&P Global Mobility, bringing a truly global perspective and deep industry insights. 𝗍𝗹𝗲𝗰𝘁𝗶𝗶𝗰, Senior Analyst, Electrification Technology Research, 𝘲𝗹𝗲𝗲𝗀𝗃, Senior Analyst, Electrification Technology, Diana Quesada, Charging Service Lead, 𝗍𝗹𝗲𝗲𝗃, Senior Technical Research Analyst, and Suraj Shetty, Principal Analyst. We are thrilled to have them with us today. I will hand over to our speakers. Welcome and thank you for joining us.
Thank you so much, Alexandra. Thank you everyone for joining us today. Today we're going to be discussing a variety of different electrification topics that we cover here in the Supply Chain Technologies group at S&P Global. And I'm going to kick it off with my domain. So my name is 𝗍𝗹𝗲𝗲𝗀𝗃. I am an analyst on the battery team here. And so we're going to start the discussion with a look at battery trends in the automotive space, given the global current context. So to start off, we've all been hearing a lot about an EV slowdown, EV demand decrease over the last year and a half, given a lot of shifts in global policy. And we have seen that reflected in a decrease in our forecast battery demand globally. So, around this time last year, the end of 2024, we were expecting to see battery demand for the light vehicle segment, the passenger cars, at around 3.4 terawatt hours by the year 2031. But we've downgraded that now. We're looking at something like 2.5 terawatt hours for light vehicles. So we're still expecting to see significant growth from now until 2031, globally as well as in individual regions, but it's just a little bit slower growth than what we were expecting previously. Now, that's for light vehicles, your passenger cars, but we also expect to see some growth in some other segments for automotive applications. We have the medium to heavy commercial vehicle segment, so think, your semi trucks, your large vans, etc., used for commercial applications. And that segment is kind of in a newer stage, kind of looks a lot like what the market for light vehicles looked like 5 or 10 years ago. So it is making up a relatively low portion of automotive battery demand, something around 7%, but it offers a really niche growing market with a lot less competition compared to what we're seeing in the light vehicle market. And then finally, we also are looking at growth in the low voltage battery applications. So these are lithium ion batteries that are replacing your standard lead acid batteries for like starter or other applications in electric vehicles. So we do expect to see growth in the installations of those lithium-ion batteries in as your auxiliary or starter batteries. But because the batteries themselves are relatively small, even a lot of installations translates to a relatively limited global demand, so around 13 gigawatt hours by 2031. Now, in terms of what this kind of context of a slowing down demand and a little bit of a stagnation kind of translates to in terms of technology trends, here we're going to look at the cathode chemistries. So on the left, we see a global picture. On the right, we're seeing specifically in China, the largest market. So globally, we do expect to see a shift towards LFP over the next few years. This reflects both a big focus on cost effectiveness, LFP being the cheapest chemistry of those batteries going into electric vehicles. And we'll talk a little bit more about cost moving forward, but it also reflects a further spreading of Chinese supply chain, especially when you look at a region like Europe, you have Chinese players, both OEMs and cell suppliers, really moving in and setting up shop in terms of production in European regions. So we see LFP increase there. You also see that high nickel, that purple piece, taking and leading future battery chemistry as well. And that has to do with just the high energy density that it provides. You can see that your green, your mid nickel is really being cannibalized from the top and the bottom. For those applications that really need your high energy density, these suppliers are going to turn toward the high nickel. Whereas if you can get away with a little bit lower energy density, LFP is going to give you cost savings and be a bit more of a better choice. These same trends carry forward with China, where of course LFP already takes up a majority of the market. We expect that to continue, but seeing that that high nickel piece come in to a bigger market share as well. What's a little bit hard to see because it's still relatively small, is you can see a little more on the right there is in dark blue at the top, you start to see sodium ion come in the 2030s. And that, of course, is going to have to do with cost, which we can get into in the next slide. So this is a snapshot from our battery price report. We have basically taken our forecast prices for some of the more affordable chemistries. We're looking at the high voltage NCM60 in blue, so that's your kind of mid nickel NCM. LFP in yellow, your NCM217. So this is also now being referred to as LMR, lithium manganese rich chemistry, by players like GM and Ford. And then in purple, you have your sodium ion. So as you can see, right now, LFP is really in a price class of its own, being driven down largely by prices in China. A lot of these cell suppliers are taking kind of razor thin margins in order to try to gain or maintain as much of their market share as possible. But as time goes on, both with raw material prices fluctuating, we've seen an increase in lithium prices recently, and LFP does have the most lithium out of any of these chemistries, so it's most exposed to that particular fluctuation, but also just technology maturation in some of these evolving technologies, sodium ion and your LMR, as they mature, those prices can be drawn down a bit. And so for sodium ion in particular, we're expecting to see price parity with LFP somewhere around 2031, 2032, and that price continuing to drop from there. And how this actually translates into actual adoption in automotive applications, we expect to see the adoption to start a little bit earlier than that. In China, that adoption is really going to come down to cost. There are some other benefits of sodium ion technology-wise, but really cost is going to be driving that adoption. But as you look west outside of China, in Europe and in North America, the other big factor outside of cost is going to be supply chain stability. And sodium ion provides the opportunity for these regions to be less reliant on China, where the LFP supply chain is already so heavily focused. And so even before some of that price parity evens out, especially in somewhere like Europe, we expect to start to see sodium ion be taken up as an option to decouple the supply chain fully from China as it is now for those cost-saving chemistries. Now, in addition to your cathode chemistry, the other big pieces of the battery technology to be looked at are your anode and then also your electrolyte. So solid state has been discussed for a long time. It's been really looked at as, this potential game changer in energy density and therefore range of these electric vehicles. But as time has gone on, we often hear about new innovations in the solid state space, but that really use and mass application of electric vehicles has continuously gotten kicked down the road, and because there are still several hurdles that solid state has to overcome. They really break down into manufacturing problems and then also performance issues. So for manufacturing, a lot of it just comes down to cost. So lithium metal anodes would be your ideal anode to use to really take advantage of the full energy density for solid state batteries. And they come with a lot of manufacturing difficulties. They're just more difficult to use in the conditions that current manufacturing is in, and they require some more expensive materials. This also has to do with conversion of current infrastructure. So the lines that currently produce lithium-ion batteries will have to be converted to manufacture solid-state batteries, and that's going to be a very costly endeavor. And a lot of these lines, especially outside of China, are relatively new or still being built right now. So to have to convert brand new lines into solid state manufacturing is going to be very costly. And then on the performance side, you have safety issues that are inherent to lithium metal anodes, and your lower ionic conductivity of solid state leads to poor fast charging and poor power performance. So we have a lot of cell suppliers and OEMs working to solve these problems right now, but it is pushing that really start of production of these solid state in EVs out a little bit further, which you can see here. So in terms of solid state battery demand, right now we do start to see your semi-solid or liquid solid electrolyte being deployed for automotive use, but that's kind of just a halfway point that really doesn't take full advantage of the benefits of solid state. And so, although we see that being deployed around now, that's not going to be like the full game changer that's expected to see from solid, which we are going to start seeing around the new decade. But as you can see on the right here, we have our percentage of total battery demand for the light vehicle batteries. And the solid in red there, even by 2037, we're only expecting it to take up a small portion of that demand, maybe around 2%, just really because of that cost. The solid state batteries are going to be reserved for your luxury vehicles, your absolute highest energy density requirements, rather than being a solution for the masses of EVs. Um, so, in the context of slowing demand, OEMs and suppliers are focusing on bringing down the cost and stabilizing their supply chains rather than chasing the highest energy density possible, like we're seeing with something like solid state. So, thank you so much. Now we're going to hear from Daniel on the outlook for electric motors.
Thanks, Gabriel. Hello, everyone. My name is 𝗍𝗹𝗲𝗰𝘁𝗶𝗰. I'm a propulsion analyst at S&P Global Mobility, and thanks for having me here. Let's jump right into e-motor trends and what we are seeing this year. So lately, we have seen increasing popularity in different types of hybrids. On this next slide, you'll see three main colors: blue one for full electric vehicles with different shades for each region, the orange for hybrids, also with different shades per region, and the red one will be for range extended electric vehicles. What we see globally is that hybrids are gaining share, while full EVs are flattening across most regions. But the overall trend is fairly consistent for now. Hybrids are gaining share because are gaining share because for a few reasons. They have broader model availability, and they feel less risky to many customers than going full EV. In China, we are also seeing a recent boom in range extended electric vehicles. Several important OEMs like XPeng and Li Auto are planning to launch REVs model this year. And it's also important to know that China has already exceeded 50% of new electric vehicle penetration. As for Japan and Korea, they are primarily betting on hybrids, not only for their domestic market, but also because their OEMs are pushing hybrid technology worldwide. That's why when you look at the top hybrid sales, consistently you will see models like the Toyota RAV4, Toyota Prius, Honda Accord, and Kia Niro, for example. All of these will directly impact what type of e-motor if each region is using. In this next graph, you can see each region and its preference by e-motor technology. The baseline today is and will likely remain permanent magnet motors with rare earths. However, supply chain disruption is affecting every region. Recently, geopolitical tensions around the rare earth elements has pushed OEMs and suppliers to explore alternatives different from neodymium and dysprosium-based magnets. Greater China controls the vast majority of rare earth processing, which for sure gives them significant influence over supply and for sure pricing for these materials. Europe in particular is trying to reduce dependence on permanent magnets, as we see in the graph, which is driving development of externally excited synchronous motors. In the other hand, North America is being impacted by the restrictions from China in response to their tariffs. So as a result, companies like, for example, MP Materials are developing new mining and processing facilities in North America region. However, this will take time, and for sure, the domestic supply of rare earth will likely prioritize national security needs uh, for United States. That's why some North America OEMs, including Tesla, for example, have started discussing permanent magnet designs with reduced or not rare earth usage at all. Induction motors are another alternative for this situation, but their performance and efficiency trade-offs often limit them to secondary drives or lower cost applications. Uh, so overall, these trends are pushing more strategic planning and tighter coordination between OEMs and suppliers, and that leads us to this next slide. Uh, Supplier dynamics we're seeing across regions and how vertical integration it's shaping the module landscape. In Greater China, for example, there is a strong preference for in-house production and strategic sourcing. The I mean, they already have this vertical integration really well established in the region, and this continue to squeeze standalone motor suppliers, especially given the China's strong control of the upstream materials. In Europe, the story is different. Historically, OEMs have relied more on strategic partnerships, but we are increasingly seeing a shift towards in-house production, mainly to secure critical supply chains. And North America is moving in a kind of similar direction as Europe. Growth in in-house production and vertical integration will be heavily policy driven. Suppliers will increase North America content to maintain access to incentives under, for example, the USMCA. And it's important to keep in mind that for US, Mexico, and Canada, uh, this year is scheduled a revision of the trade agreement. So many of us are watching closely because EVs and the broader electrification transition are expected to be a key topic in this revision. And this can basically change the field for the regions and for the players. Finally, Japan and Korea are likely to remain more hybrid leaning in the near term, which reduces the urgency for aggressive motor-only vertical integration compared to other regions. It's also important to keep in mind that vertical integration has become increasingly popular, not only because it helps secure a steady supply chain, but also because it speeds up the project development timelines. And just to summarize all of what's happening with the motor world, first of all, hybrids are gaining market worldwide while full EVs are fluttering a little bit. Hybrids are favored for broader model and lower perceived risk. In second place, permanent magnet motors remain the baseline, but rare supply constraints are driving Europe towards ESM designs. North America is exploring mining and reduced rare earth dependence, while Greater China will keep control over rare earth processing. And in third point, Greater China pushes in-house production and vertical integration. Europe and North America are moving between strategic partnerships and internal manufacturing to secure supply chains influenced by policy and trade agreements, while Japan and Korea stay hybrid focused. Thanks for your attention. Now let's move to another important topic, power electronics, with my colleague Abhishek.
Thank you, Daniel, and hello everyone. Welcome to the next section where we talk about the key power electronics trends and the latest developments in this field. I'm Abhishek Parashar, and I'm a senior research analyst with the electrification technology team at S&P Global, and I lead the power electronics components research, tracking and evaluating the latest technology and supply chain trends within the electric vehicle ecosystem, primarily related to inverters, DC-DC converters, and onboard chargers. Let's quickly jump into the topic now. So this slide here presents an outlook of the automotive power electronics industry, talking about the key trends and highlighting the latest developments related to them. Let's begin with the first one. Among the latest innovations and trends in power electronics, wide bandgap semiconductors stand out as a frontrunner, promising significant advancements. With advantages including high switching frequencies, lower switching losses, smaller size, lightweight, and reduced cooling efforts. WBG material based switching devices enable trends like high voltage platforms, rapid charging, etc. In the past year, WBG materials have witnessed acceleration in adoption with silicon uh, carbide price erosion and gallium nitride becoming production ready for medium voltage applications. We'll talk about this in detail in an upcoming slide. The next is the introduction of high voltage platforms that offer various advantages. Since the voltage increases, with it, the current level drops, which requires thinner conductors, thus saving copper weight and cost. That enables smaller battery size, lightweight, and it also lowers the losses in form of heat and thus better efficiency of the system. High voltage also plays a pivotal role in faster charging rates. In the past year, various Chinese OEMs have launched vehicles with megawatt charging capabilities enabled by these high voltage platforms, with the system voltage as high as 1,000 volts. Next, the higher levels of powertrain and power electronics integration offers higher efficiency, cost, and weight synergies. Components integration will reduce high voltage wire harness lengths, thus reducing weight, cost, and losses. In the past year, we have seen Greater China driving higher levels of powertrain integration, all the way up to as high as 12 in 1. Along with the drive unit integration, another upcoming trend is the higher level of secondary integration, where power electronics, electrical, battery, and thermal components are integrated in a separate layer of integration other than the drive unit. The last one is the shift in sourcing strategy and supply dynamics. OEMs currently are reevaluating sourcing strategies for power electronics as electrification volumes scale, and there are complexities on technology and supply chain and the demand fluctuations as well. The focus has shifted from pure cost competition towards technology access, supply security, and long term strategic control of critical components such as silicon carbide MOSFETs, power modules, and control and design softwares. Over the past year, we have seen accelerated vertical integration, primarily driven by Greater China, with OEMs increasingly bringing inverter design and power module packaging and even semiconductor sourcing in house. Several global OEMs are also internalizing inverter development while maintaining strategic partnerships for semiconductor supply. This hybrid sourcing model enables differentiation at system level while mitigating capacity and geopolitical risks. So let's move on to the next slide now. First and foremost, let's take a look at how wide bandgap semiconductors are enabling the high voltage platforms of future, which offers numerous benefits to end users, including high range, faster charging, and low costs. As we observe the current market landscape, there's a clear and a decisive shift towards WBG materials, especially silicon carbide, as industry shifts towards high voltage platforms for the benefits as we just discussed. This will aim at a widespread adoption of electric vehicles. This transition is not merely a trend, it represents a fundamental change in how we approach power electronics for medium to high voltage applications. To take a look at the data, the voltage classification that we have done here is crucial to be understood. The low voltage, we have defined it anything below 72 volts. Then medium voltage ranges from 72 volt to 600 volt. And in high voltage, we have anything above 600. By 2036, projections indicate that over 55% of the high voltage components will be based on silicon carbide. This is a remarkable shift considering that silicon carbide is expected to dominate high voltage inverters with a staggering 64% of market share, as well as over 50% of high voltage DC-DC and OBC share. This dominance it underscores the preference of silicon carbide due to its superior performance and efficiency characteristics. There's another important aspect to this. While WBG materials like silicon carbide and gallium nitride are increasingly being adopted for high to medium voltage applications, it's important to acknowledge the continued relevance of IGBTs, which remain a staple in low and medium voltage applications, where IGBTs have proven performance and cost effectiveness that makes them invaluable. Let's quickly jump to the next slide now. Talking about WBGs and their adoption and the acceleration in their adoption in the past 1 year, let's take a quick look at the latest developments surrounding these two materials. Firstly, talking about silicon carbide, in the past year, the prices of silicon carbides of discretes have declined rapidly, primarily driven by excess manufacturing capacity, new wafer supply coming online, and intensified competition, especially from mainland China. So, due to this, the cost differential between silicon carbide and silicon power devices has continued to compress as the technology matures. Talking about the prices, in general, as a rule of thumb, by 2026, silicon carbides are typically priced at around 2 to 2.5 times the cost of equivalent silicon discretes, compared to 3 to 4 times in 2025 and around 10 to 12 times a decade ago. While module level pricing varies significantly by packaging, current rating, and integration levels, this generalization and the overall trend points to silicon carbide steadily approaching cost parity thresholds required for mass market adoption. Talking about the next material, gallium nitride, there is also an acceleration in the gallium nitride uptake, which is expected to scale meaningfully post 2027, initially in onboard charger and DC-DC converters. This is primarily supported by the improving reliability credentials and cost trajectories for gallium nitride. Greater China OEMs and tier ones are supporting this acceleration. Let's jump quickly to the next slide now. Taking a closer look at another key development and a trend in power electronics, the system integration trends, and since Greater China has been a leader of these trends, we will take a look at this data using Greater China as a focal reference point. In the world of power electronics, the level of integration is significantly shaped by the components provided by suppliers. Notably, the suppliers with specialized knowledge in propulsion and power electronics are crucial for advancing the integration of X-in-1 systems. Greater China and the OEMs and suppliers are pushing the limits of system integration further every day, which also supports Greater China's global ambition of Chinese OEMs and tier ones to take a major share of the global EV supply chain. Here in the chart, we have segmented the volumes for various system integration definitions: standalone, two-in-one, three-in-one, and the last one is X-in-one, which is used to depict anything above 3-in-1 and goes all the way up to 12-in-1. We have three charts here. The first one is global, which excludes China, Sorry. The next one is just for Greater China, and then the third one is global, excluding China. Taking a look at the data in 2025, X-in-1 systems have an impressive 22.18% of the market share in Greater China. This is a stark contrast to the global market excluding China, wherein X-in-1 systems are projected to hold only around 1%. This indicates a stronger regional inclination towards higher integration level. emphasizing China's capability to lead in this domain. Another trend is the rampant growth of the three-in-one systems, which emerge as a dominant trend globally and in Greater China as well, accounting for more than two-thirds of the market. So let's jump on to the next slide quickly. Okay, now with the next graph, we delve into the details, going beyond the drivetrain integration and taking a look at the secondary layer of integration. As we just discussed, the trends in system integration and the benefits and the global analysis of the same, it becomes very relevant to take a look at how the secondary layer of integration is developing, including the power electronics, electrical, battery, and thermal components. As you can see from the previous graphs, the most important trend emerging in system integrations is the stellar rise of three-in-one integration levels. Deeper analysis show that along with three-in-one in drivetrain, at secondary level of integration, DC-DC converter integrated with onboard charger is a prominent trend currently and is projected to make up nearly 50% of the market by 2037. Notably, over 75% of vehicles with three-in-one systems adopt this level of integration, which has DC-DC and OBC in it, which means motor, inverter, and transmission integrated in the drive unit, along with DC-DC and OBC integrated as a separate layer of power electronics integration. In the past year, we have seen several newer designs creeping in, incorporating power electronics with the components like battery management, thermal, and also thermal related components. Let's quickly jump on to the next slide now. So, talking about the latest trends in global supply chain related to power electronics, we will focus on this data from inverter switching device supply dynamics. For inverters, several global OEMs are internalizing the design and development to have more control on the design part while maintaining strategic partnerships with semiconductor suppliers. Another important trend surrounding the traction inverter supply chain is the supply dynamics of the power modules, the data related to which we have on the screen. This hybrid sourcing model enables differentiation at system level while mitigating the capacity and geopolitical risks. In this slide, as we analyze the data, we can see a significant declining trend of in-house production of inverter power modules. This shift underscores a growing reliance on supplier partnerships within the industry. In fact, it is projected that in-house production will decrease from 57% in 2025 to 47% by 2037. This trend highlights the industry's move towards outsourcing, which is becoming increasingly prevalent. Furthermore, as we observe a notable change in the market share of suppliers, Tier 1 suppliers are currently expected to hold 70% of the outsourced market in 2025, but this figure is projected to decline to 59% by 2037. Meanwhile, Tier 2 suppliers such as Infineon, STMicroelectronics, and and onsemi are gaining traction, increasing their market share. This shift indicates a significant evolution in the supplier landscape, where Tier 2 suppliers are becoming more influential. So that's it from my side. Thanks for your time. I'll hand it over to my colleague Diana now, who will talk about vehicle charging technologies. So over to you, Diana.
Thank you, Abhishek. Hi, everyone. Thanks for joining us. My name is Diana Quesada. I'm analyst based in Mexico, and I'm going to talk to you a little bit about what has been going on in the past year, what have been the milestones in 2025, and what can we expect in the upcoming years on the side of vehicle charging. And I want to start with a little refresher because this has been addressed or referenced by my colleagues previously, but I want to go again a little bit in depth. as it has been pointed out by my colleagues, EV adoption has continued to rise globally, but growth has become more uneven, especially across regions, and slower in some mature markets as incentives tighten, affordability constraints persist, and charging and model availability lag, especially in 2024 and 2025. Tariffs and escalating trade tensions, especially around Chinese made, especially around BEVs, so battery electric vehicles, especially the ones that are Chinese made and batteries also Chinese made. Uh, these tariffs and trade tensions have reshaped prices, supply chains, and it has changed which models qualified for incentives, and this has influenced sales mix and growth rates. However, despite these headwinds, EV demand remains structurally strong, with the fastest momentum focused or concentrated in China, and continued in the expansion in Europe and North America as well, but a little bit more policy dependent. Um, Now, uh, we want to know a little bit what is going on behind this current status and the forecast of these numbers. And well, these are the forces that are shaping the growth of the electrical vehicle market. First of all, obviously, the role of the government is of very high importance here, both in terms of the deployment of charging infrastructure and the transition to electric vehicles. Um, Incentives are designed to stimulate EV adoption and support the development of charging infrastructure. And this has a particular focus on making the benefits accessible to, especially to low-income communities. Um, Different markets employ a different range of incentives and tax advantages to drive the demand for electric vehicles. However, the impact of these measures varies widely between regions, underscoring the need for customized approaches for effectively promoting the EV uptake. Um, I think my colleague Gabriela did mention the advancements in vehicle technology, especially in battery technology, which is of course the main enabler of uh, of the vehicle development. However, I do want to focus a little bit on the impact these technology advances have in the the openness of consumer openness to integrate electric vehicles in their lives. So um, battery advancements in battery capacity enable longer driving ranges, and this helps to alleviate range anxiety among consumers. Improvements in battery chemistry are also enhancing durability and safety, which as well increases the consumer trust in these vehicles. And this is very important because range and charging are two of the main constraints for consumers to effectively adopt electric vehicles into their everyday making decisions. Um, so these innovations effectively broaden the appeal and accessibility of EVs to a wider audience. Recent progress includes major breakthroughs that have been mentioned before in solid state and sodium ion battery technologies. And this is very important for consumers not to fully understand it, but to understand the impact this has on range and charging and the charging experience. And finally, the expansion in charging stations, because obviously a comprehensive charging infrastructure is crucial for the widespread adoption of battery electric vehicles, especially in urban areas and major highways. These are now featuring more fast charging stations, which in turn makes longer journeys possible, and it really eases concerns about the driving range, which again, it's one of the main concerns for potential EV users. Modern charging stations can power up vehicles in a matter of minutes. Doesn't take, it doesn't necessarily take hours, And this is an attempt to offer convenience that more closely resembles conventional refueling process. So the process of just going to fill up your gas tank, it's what this is trying to mimic. And as the charging network becomes increasingly dependable and accessible, more consumers are viewing BEVs uh, as a practical alternative to traditional cars. Uh, Governments and associations are also uh, uh, showing a lot of commitment for the deployment of public and semi-public fast charging infrastructure. And this is mainly because we as a society are beginning to understand the actual costs of deploying fast charging infrastructure that go beyond the station. I think for a lot of time, people weren't really, and with people I mean a little bit government and associations, there, there wasn't really an awareness of the costs of the installation and grid connection specifically, because everyone knew that stations, especially fast charging stations, are very costly. But now there's a better understanding of the costs associated to the grid connection, which in many cases depends on the region, the country, and the grid. But in many cases, the cost of connecting to the grid is more expensive than the station itself. Um, for example, these are, as you can see in this slide, these are the top countries that offer the highest incentives for DC charger installation in 2025. And at the top, as a kind of a surprise, because they hadn't offered this as high as an incentive previously, but France actually added, as part of their Avenue program, a really record-breaking incentive with over $1 million, so 960 thousand euros, and this really shows the country's commitment or the government's commitment to to the to the endeavor. United States has been more consistent with offering these types of incentives, and even though there is on a federal level a lot of uncertainty regarding the incentives that are going to be offered countrywide, there is a lot of efforts individually by states, and this is why the second the second highest incentive is offered specifically in the state of Pennsylvania as a cash incentive for setting up a fast charging station. And several other countries are also beginning to understand and act accordingly. And in turn, there is a lot of increase of fast charging stations deployment around the world, specifically or especially in China. In this graph, what you can see on the numbers on the left and the block and the yellow blocks are the Chinese the deployment forecasted for until 2034 for China, and on the left side, you can see the ones for Europe and North America. And this is divided as this because the difference, the gap is so big that it made more sense, or it creates a better understanding to have it separated like that. China's deployment of fast charging station has been accelerated rapidly, and it has been fueled very substantially by central government subsidies and coordinated national policy agenda that really prioritizes electric vehicle infrastructure. And this have enabled China to establish one of the world's most extensive and accessible charging networks that supports both urban and long distance travel for EV users. And in contrast, Europe and North America are really intensifying their efforts to expand charging networks because they recognize the need to match China's pace. The governments in these regions, Europe and North America, are rolling out national level incentive programs such as grants, tax credits, public-private partnerships, and this is all an effort to to support the investment in fast charging infrastructure to close existing gaps in coverage across these regions. Another very crucial thing that happened in 2025 has been the increase in peak DC charging power. That, as you can see in this graph, China currently is at the forefront of innovation in charging technology. And in this case, lead manufacturers such as BYD are pioneering in solutions that are taking a toll or creating a bigger gap between the peak DC charging power from China and North America. You can see the vast difference between that one from BYD as opposed as, for example, Audi or Ford. And this is something very important because this really marks a major technological leap with charging stations capable of delivering extremely high power outputs. And this allows passenger cars to recharge in a matter of minutes. It's especially impactful for the long haul with a rapid turnout of charging times being critical for this endeavor. And finally, let's quickly address the increase in charging power, not only being not being the only way for companies to innovate and make the charging experience as close as possible to the refueling experience of a regular gas tank. For example, these innovations are somewhat divided regionally, and in the case of wireless charging technology, it's getting greater traction in the Western hemisphere, with Porsche, for instance, announcing last year that its 2026 Cayenne electric model is going to feature a wireless charging as a premium option for the vehicle. And this is going to be followed very closely by other brands, but definitely focused on the Western hemisphere. And in contrast, Chinese are prioritizing solutions that minimize charging time, which aims to replicate more of the way of refilling a traditional ICE vehicle. And they try to do this with solutions or innovations like battery swapping and megawatt charging. This is central for their approach, and this allows users to very quickly recharge or replace the batteries on the road. And a little bit more global based, bidirectional charging is the technology that is anticipated to become most widely adopted across all markets. And even though this doesn't interfere or alter the actual charging process, this does in fact offer a lot of post-charging benefits, and as it enables users to supply power back to the grid or their homes, and it enhances the overall value of flexibility of owning an electric vehicle. Finally, as a very brief conclusion, 2025, there were several technological advancements that are redefining the electric vehicle landscape, including commercialization of megawatt charging, wireless charging, and these innovations are designed to address common consumer concerns such as charging speed, convenience, and overall charging experience. At the same time, inventive approaches to EV infrastructure and technology are emerging worldwide, and this really reflects the dynamic nature and industry and its responsiveness to the evolving market demands. And this was it for me. Very happy to take your questions at the end, and I'm going to leave you with my colleague Suraj for the next portion of the webinar.
My name is Suraj Shetty. I'm the principal analyst here at S&P Global for automotive thermal technologies. And the last part of the presentation, I would like to give you a snapshot of what thermal management technologies in EVs look like currently and where we think it's going towards. So move to the next slide, please. The next one, sorry. Yeah. So this slide aims to sort of set a picture and depict the evolution of thermal management in EVs across what we believe are three pivotal phases. So if we look at the first one, the first phase was mainly driven by focus on component and hardware system design, where the focus mainly used to be on the individual component performance and cost sensitivity. So basically the sizing of the radiator, the airflow, etc. That was what the focus was on. And this phase usually used a simpler air cooling or an individual coolant and refrigerant loops, and generally tended to borrow a lot from legacy automotive thermal management. The mid phase, the one in yellow, focused more on integrating the various individual thermal circuits, the heat recovery and modularity. So what it means is that instead of individual components sort of thrown together into a circuit, the components were increasingly assembled into integrated thermal modules. I will cover this more in detail in the coming slide. And this approach has major benefit in terms of performance optimization and packaging. The next phase, which we expect, is to continue the hardware design refinement and the modular integration. But we expect it to increasingly turn towards artificial intelligence, which acts as a brain overlooking the system. And AI will allow the BMS, battery management system, which also includes the thermal management, to transition from the current reactive-based system to a more proactive, predictive-based system. Move to the next slide. Yeah, I think it's pretty common knowledge now that EV batteries are extremely sensitive to temperature. Pretty much every topic around every webinar, every presentation sort of talks about it. And an optimized thermal management system is crucial to a battery's performance, also to its service life and the safety. And as you can see in the slide, modern EVs are mostly offered with sophisticated coolant-based thermal management systems. Even developing EV markets like India sort of moved away from the initial experiments with air-cooled battery solutions. And the primary drivers for this design direction is very simple. It's been the growing battery power and size, the high-density fast charging, and the safety regulations. Another main driver is the increasing integration I spoke about. The various individual coolant circuits can be interconnected very easily via a system like what Tesla uses, which is the 𝗲𝗲𝗲𝗀, it allows more efficient heat recovery and performance optimization. Now the demand for coolant, the earlier slide. Yeah. The demand for coolant-based thermal systems and associated components is mainly led by Greater China, considering that they are the largest market and producers for EVs, and it's followed distantly by Europe and North America. Now, when it comes to air cooling, we see that there is still some demand there. Now, this demand is mainly restricted to the budget EVs with smaller batteries or full hybrids, which tend to have 5 kilowatt-hour batteries. When it comes to refrigerant-based cooling systems, that remains a niche design choice even now. Move on to the next slide, please. Now, when it comes to motor cooling, as you can see, the cooling strategy for e-motors is fairly sophisticated. It's mainly liquid cool based, and it's expected to remain so going forward. And for coolant-based e-motor cooling solutions, it's China which leads the demand, followed by Europe. Now, when it comes to oil-based e-motor cooling systems, the demand is again led by China. But the other major demand generator for this trend is North Korea and Japan, Korea, and North America. We can move to the next slide, please. Yeah. Now, when we talk about thermal management, in addition to the batteries, the other main challenge we look at is maintaining the thermal parameters of the passenger cabin. Now, earlier EVs basically borrowed the HVAC design from existing internal combustion engine vehicles, which we classify as a conventional HVAC. Basically, what it did is it just added an electric heater to handle the cabin heating duties and swapped a belt-driven compressor with an electric one. It's not the most energy-efficient solution when it comes to real-world driving range. And in the real world, we used to see a drop of up to 40% when the cabin was heated or cooled to comfortable temperatures in extreme ambient conditions. Now, in mature EV markets, heat pump-based systems is already pretty much a de facto choice. We see an increasing demand there. And it's either offered as a standard in premium segments or as an option in the lower segments and trim options. And as you can see in the slide, the demand for heat pumps is mainly led by Greater China, where sophisticated thermal management solutions is pretty much a standardized solution now. And it's followed closely by Europe. And European OEMs are increasingly offering heat pumps as a solution. We recently saw Mercedes-Benz in its EQE offering heat pumps as standard fitment across trim levels. Now, heat pump is a sort of an umbrella. Sorry, just to it's sort of like an umbrella term, and the configuration and complexity can vary based on design strategy, cost targets, and very importantly, the refrigerant which is being used. Next slide, please. Yeah. Now, as I spoke about integration of individual components into thermal modules. Now, when it comes to thermal modules, we classify it into 3 different types. So first would be the coolant module. So what it basically does is that all the components within the coolant loop, it aims to bring it together into one single module. So that would be the reservoir and the manifold. Similarly, for the refrigerant module, it would be the hose assembly and the manifold. And a dual module is basically which combines the coolant module and the refrigerant module, into one single module, a much more sophisticated system. If we can move to the next slide, please. And as we can see, the sort of a preferred choice for a module solution is mainly a combined one, which is a coolant plus a refrigerant module. And this demand is mainly led by the Greater China region, where integrated modules are being increasingly standardized by the OEMs there. And Europe is the next largest market for these modules, though it trails the Chinese market by quite a bit of a margin. You can move to the next slide. Yeah. So if I could just call back to the first slide, as I mentioned, the guiding ethos of thermal management design has evolved, and accordingly, the control strategy for the same has also evolved. Now, it has evolved from the early reactive hardware and fixed controls to the current logic controllers and PID regulations, which offer multiple reactive optimization maps. The next step in thermal management, which we believe is expected to be with AI taking over the decision making in real time and making the solutions predictive rather than reactive, which we see currently. Next slide, please. Yeah. So I'll sort of go through each AI-led solution one by one. The first one I would like to touch upon is the route-based predictive conditioning. And this is the most mature of the AI thermal management control solutions, because it sort of borrows from the existing, it builds on existing telematics. To give you a use case solution, batteries have a Goldilocks zone for temperature. So if you fast charge a cold battery, you risk lithium plating. If it's too hot, you accelerate degradation. By using GPS data, the car can either preheat or pre-cool the battery before you arrive at a charger. So the battery is ready to be plugged in without compromising. And another case is that the AI doesn't just wait for the battery to get hot. If the GPS shows a steep mountain climb or a high-speed highway stretch while you're driving along, the management system will sort of pre-cool the battery in anticipation of the upcoming heat load. No, it's sorry, we can stay on the previous slide. Yeah. So the next sort of thing I would like to touch upon is the digital twins and cloud-based analysis. Now, by leveraging a digital twin, which basically is sort of like a high-fidelity virtual replica of the battery which is uploaded on the cloud, the manufacturers can unlock insights which are physically impossible to measure in real time via sensors and actuators on a single vehicle. No. And you cannot have physical sensors placed inside every cell. So what AI models do is it can use the surface temperatures and the current draw to estimate the internal core temperature, which is where the real damage happens. And by it then uploads this data to the cloud, and then the manufacturers can then compare one vehicle's battery data against an entire fleet's worth of data to predict the state of health. And when you combine the two, you sort of thermal management sort of shifts, as I said, from reactive cooling It's basically turning the fan on, letting the coolant, switching on the coolant pump, etc., to more predictive based thermal control. And the last one is the most cutting edge of the previous slide, please. Yeah. The last is the neural control network or AI-based battery management system, which includes the thermal side. Now, this is the most cutting edge of the three, and it moves away from the rigid rule-based logic which we see currently. And so, for example, the PID controllers which we see currently, it struggles with non-linear nature of battery chemistry. For example, the thermal runaway is not a predictable straight line, and neural networks can sort of learn the specific thermal fingerprints of a battery pack. Another use case is that as the battery ages, its internal resistance changes. A neural-based BMS can adapt its cooling strategy over a period of time, taking this degradation into account. Can move to the next slide, please. The key, to summarize it or give you the key takeaways, we see that the complex coolant and refrigerant-based battery thermal management is becoming the standard globally across markets. We see increasing integration in terms of thermal modules, and that is becoming more of a de facto solution, especially in the more mature advanced markets. The thermal management is expected to evolve from reactive cooling hardware-based solutions to more AI-driven controls, making decisions in real time, increasing optimization. And the last point I would like to touch upon is that the heat pump adoption is pretty much standard on BVs, even though the configuration varies. Thank you. Handing over back to Daniel.
Thanks everyone for the amazing information. And just to summarize all the ideas and key takeaways in how we see 2026 for this electrification landscape, we prepared just these simple bullets. So for battery, the electric vehicle market is facing a slowing adoption, tariffs and trade tensions, prompting OEMs and suppliers to shift towards cost-saving technologies. Energy density optimization is still being worked on, but is taking a backseat. For the e-motor landscape, hybrids and REVs propulsion systems adoption is rising while battery electric vehicles growth stalls, prompting regions to shift e-motor strategies from permanent magnets to different alternatives. And they are accelerating the vertical integration to secure supply chains and reduce reliance on these rare materials. For the power electronics is being reshaped by accelerated wide bandgap adoption, supported by falling prices and competition. High voltage platforms like 1,000 volts class, enabling faster charging, higher levels of integration up to 2-in-1 architectures, and increasing OEM verticalization of inverters development while maintaining a strategic partnership for semiconductor supply. For vehicle charging infrastructure, within the past year, there have been several development that continues shaping the EV market by addressing users' concern and improving the charging experience. Megawatt charging, for example, wireless charging and charging station deployment. However, incentives to deploy charging infrastructures are key for the continued evolution of the EV landscape. And lastly, for thermal management, it's evolving from reactive cooling hardware into a predictive AI ecosystem that optimizes vehicle range and user time. So thanks everyone for your attention, guys. It's been a pleasure. If you have any question, write it down in the chat, and please contact us to have a deeper discussion about this topic. Our contact info is in the last slide. And we're going to share these slides with you for sure. So I don't know if we have time for a question, Alexandra, or
Yeah, we are already 5 minutes over the time. So, as you said, if anyone has any questions, please get in touch with us directly or directly with the speakers. I would like to thank you for such a compelling and insightful presentation. There's clearly a lot to unpack, and I know our audience has gained valuable takeaways. I would like to thank our speakers for an excellent and insightful presentation. I trust our audience has gained valuable perspectives and practical takeaways from today's discussion. A special thank you as well to everyone working behind the scenes. Your efforts are what make sessions like this possible. As mentioned earlier, the recording will be available on demand via our website. I'm pleased to share that registration for CWIEME Berlin 2026, taking place from the 19th to the 21st, is now open, and we encourage to secure your place and take full advantage of the opportunity to connect in person at the global home of coil winding. I very much look forward to welcome you and see you in Berlin, and thank you again for joining us, and have a wonderful rest of the day. Thank you.